Hey guys, welcome back for another chemistry lesson. This lesson is going to be about acid-base reactions. Before we talk about acid-base reactions, we probably should talk about acids and bases. So let's start with acids. So acids are molecular compounds that ionize when they dissolve in water and spit off a hydrogen ion. And the percentage of the acid molecules that do this varies from one acid to another. Acids that ionize virtually 100% of the time are called strong acids. They are classified as strong electrolytes. If you need to sort of be reminded what that means, go that way, up into the cards and watch the video on solutions so that you can review that. So an example of a strong acid would be hydrochloric acid, HCl. So pretty much 100% of HCl's, when dissolved in water, break up into H pluses and Cl minus. This guy right here, and actually, oops, I wish I had done that in a different color. Anyway, I'm going to do it in a different color. That right there is the piece that makes it an acid. This is what makes something an acid. All right, we increase concentration of H pluses. All right, acids that only ionize part of the time, which are classified as weak electrolytes, are weak acids. So that would be, for example, hydrofluoric acid, HF, where we get H pluses and F minuses. You'll notice between the two that we have this arrow, single arrow here, and a double-headed arrow here. This indicates to us, if we can't remember if it's a strong acid or not, strong acids will proceed to completion the separation of H pluses and Cl minuses. HF exists in equilibrium because only a small percentage of the HFs break apart. So, strong acids break up 100% of the time. Weak acids break up a percentage of the time. Right? Now, again, these are substances that produce a H plus in aqueous solution. This is the Arrhenius definition, which is the only one that we're really going to talk about in this course. So in solution, we don't actually see H plus. That's not how it exists. In reality, what happens is the HCl kicks off this H plus and then it goes and finds a water molecule to bond to. So if I could look under a microscope and see what is in solution, it's not H pluses, it's hydronium ions or H3O plus. So it's, tagging along with the water molecule. Now, I've been giving you binary acid examples, HCl, HF. But there are also polyprotic acids that contain more than one ionizable proton and release them sequentially. So an example of this would be H2. I swear that's a 2. This is terrible. I'm very bad at writing on my mouse tracker pad. There we go. H2SO4, right? So now we have 2 hydrogens that can break off. So that would be a polyprotic acid. Poly meaning many, protic talking about the proton or the H plus that pops off. So the first ionizable proton on a polyprotic acid is strong, and then the subsequent ionizable protons, in this case the second hydrogen, is going to be a weak proton. And then on the opposite side of that, we have bases that produce OH ions in aqueous solutions. So here we have sodium hydroxide, and when it dissolves, we've got sodium ions and hydroxide ions in solution. Now, according to this definition, the Arrhenius definition, bases increase the concentration of OH ions in solution. Some bases will do that directly. So that NaOH that I showed you, when it ionizes and dissociates in solution, we get that OH that pops off. So the more NaOH I have, the more OHs I get. However, there are also Some bases, like NH3, which is ammonia, do this instead of, see, there's no there's no O here, right? Instead of like releasing an OH into the solution, what they'll do is they will react with a water, remove a hydrogen off of the water, and what is left is the second hydrogen and the oxygen. So here we've got ammonia reacting with water, and what we get is an ammonium ion, and then instead of two H's, there's now one, so I have OH minus. Either way, what is happening is an increase of the concentration of OH ions in solution. Now that we know about acids and bases, let's talk about reactions between them. In an acid-base reaction, we have our hydrogen ion from our acid and our hydroxide ion from our base, and what they do is they react and make water. And when they do that, what we have left is the anion from our acid and the cation from the base. So HCl and NaOH, I've got, let's see, highlighter, my H and my OH come together to make H2O, right? But then we've got leftovers. We've got our chlorine and our sodium. They also come together to make sodium chloride. So this acid-base reaction is a neutralization reaction where we are eliminating the stuff that makes it an acid or a base by creating water, which we see here, and the byproduct of that is also a salt. All right, so here we can see what we've got. We've got our hydronium ions and our chloride ions, our sodium ions and our hydroxide ions. And then when we mix them, what we get is, you can see in the background here, waters, and then our Na and Cl ions are in solution. Now, these reactions, like I said, are called neutralization reactions because the acid and base neutralize each other's properties. Here's an example of this. This is nitric acid and calcium hydroxide. What happens is we get our water from our H and our OH, and then our calcium and our nitrate react with each other to give us aqueous calcium nitrate. The net ionic equation for any acid-base reaction is, well, not any. For an acid-base reaction is hydrogen ion plus hydroxide ion gives us water, as long as the salt that forms is soluble in water. So if you need to review this about solubility, go back and watch the video on solutions. I'll put a card here again so that you can review that. But again, it has to be soluble in water in order for this to be the net ionic equation. So, some common acids and bases that you should familiarize yourself with. Hint, hint, students of mine. You need to know that these are the 6 strong acids. These are the 5 strong bases that you need to know. And then some other ones that you should probably be familiar with. You've got formic acid. The really big one that you need to be familiar with is acetic acid. We see this one a lot in general chemistry. That's just the acid that's in vinegar. All right, so a very specific type of acid-base reaction that we can use to quantify specific concentrations or to analyze types of reactions or types of acids is called a titration. So, a titration is a lab procedure where a substance of a solution of known concentration is reacted with another substance of an unknown concentration. So the setup is known, unknown, and we're dripping the known into the unknown. There's a diagram on the next slide. So what happens is we have this reaction happening, and we use an indicator, which is a dye that changes color dependent upon the pH of the solution that we have. So depending on what acids and bases you're using, you'll want to use a specific pH indicator. But the idea is that it will change color when we reach the equivalence point. So the equivalence point is the point in the titration when our H plus and our OH minus are exactly in their stoichiometric ratio. So in the case of NaOH and HCl, they have to be in a 1-to-1 ratio. So when they are exactly 1-to-1, that would be the equivalence point. And that is the completion of the reaction. So I will have another video, I'll link it here, where I talk about how to do the math with acid-base titrations. So I would suggest going and watching this. I will also address it in class, but this is a really, really important method for analyzing chemicals in a general chemistry lab and beyond general chemistry. So here is the setup. This is what we call a burette, and this is our known concentration. This is called the titrant. And so we are going to titrate the titrant, let it drip, into our unknown, which is our analyte, right? So I don't know what concentration this is, but what I do know is that when OHs from my known equal H's from my unknown, then the pH indicator changes color. So by using what we call the end point, which is sort of the qualitative version of an equivalence point, we can find that, and because we know how much of this we put into here, we can figure out how many H's we had here. So here in this titration, we've got NaOH being added to dilute hydrochloric acid, and when the NaOH and hydrochloric acid reach stoichiometric proportions, which is that equivalence point, the phenolphthalein, in this case, that's why it's pink, indicator will change from clear to pink. This will be different depending on what acid and base combination you're using, and therefore what indicator you're using. But when you're using NaOH and HCl, you use phenolphthalein, and it turns from clear to pink. But the idea is, because we know the concentration and the volume of this that we used by the end, we can figure out the concentration of this because we know the volume we had, and now we can figure out using stoichiometry.